if people and robots could work together happily, it would be happening here in this lab. So we're interested in how we can have robots collaborate in the home, in the office, and how we can do that naturally.
I think one thing that typifies pretty much every project here is that there is a physical user interface to the robot.
Robotics can be so useful to human society. You can get them to do the dirtiest, the dangerous, and most repetitive jobs. And if you can easily program a robot to do that using very natural languages and movements, then I feel like we've achieved something.
I'm studying human balance, so we're using our large motion platform there to create a balance simulation and to study participants on there, how they balance, what they use to balance, their vision and so on. And we're trying to figure out all the different methods that they use to do that.
Basically what we do in the lab is construct whole mechatronic systems. So basically everything from the actuators that are going to be moving whatever mass that we're interested in, to the sensor acquisition hardware, to the software that's involved, to the power amplifiers that are actually driving the actuators. So what we do is we look at the entire system from a controls point of view, and also a metrology point of view. The rotary axial spindle here, this was developed as a prototype for a silicon wafer grinder for basically next generation computer chips. The current generation is built on 300 millimeter diameter wafers. The next generation wants to be 50% larger diameter. They want to be 450 millimeters. So you need a better machine, stiffer machine, stronger, and that's where we come in.
There's always high demands for high accuracy and precision machining. So in the area of control, we need to have an accurate control system and to have the machine manufactured.
Beforehand, if you can design the process, like if you can optimize it properly using the knowledge, the know-how that we are trying to develop, we are developing in this lab, it will make it more cost efficient and time efficient at the same time, because in the industry they usually use trial and error.
Conventionally, the industry uses a chemical process to produce the very small feature workpiece, but it's very limited to like the silicon materials and only for plain geometry features. By using the mechanical removing process, we can use a micro milling to be compatible with, for example, a lot of materials, for example, aluminum, steel, or titanium. And we also can produce a lot of geometrical features, for example, like curve, cavities, and so on.
I'm researching the integration of micro-electromechanical systems, which are really small devices, with medical implants. So basically to help medical implants heal faster. For fabrication, we use the fabrication facilities in the clean room in the Ampel NanoFab facility. And in this lab here is where we use basically microscopes, vibrometers, profilometers to characterize our devices. By making devices smaller, the cost of mass production comes down. You can integrate them with other devices, for example, use them as sensors inside the body, in cars. So basically, miniaturization has many benefits, and that's what people who are studying in MEMS do.